Thank you, everyone. Today we are going to talk about the rainfall anomalies from climate hazard group infrared precipitation with station data shelves. So we all know, we say that rainfall anomalies are derivation of rainfall from long run average. They are useful for identifying wet and dry periods, which can be linked to climatically influenced patterns such as flooding, river flows, and agricultural production. So we all know that all this process is under agriculture and food security. When we're talking about food security, we talk about last week, we talked about phenology. We know what is phenology already. Now we are talking about the rainfall. Why rainfall added to when talking about agriculture and food security? We know that the rainfall anomalies are known to have deleterious impacts on agricultural rates. It's very important. When there's no rain, there's no food. So we are trying to have all the parameters that will allow us to be able to confirm or infirm that there's insecurity in foods or there's security in foods. Okay, so the traits of food insecurity has increased as a result of the phenomenon of climate change related to climate change in rainfall. The rainfall is a key factor of crop production. Moreover, rainfall provides the much needed moisture that stimulates the regrowth of grasses and facilitate the growth of vegetable series, crop, and fruit trees. So during this work, we are going to, the description of work is in the real world example. We calculate the rainfall anomalies for a selected African countries using the 5th monthly rainfall dataset. Now our own here. So we have the formula of standardized anomaly, that is X minus M over S. The X is the seasonal mean, M is the long-term mean, and S is the long-term standard deviation. This means we need a long-term reference period, M, our M. That is a parameter related to periods, time, and the period of interest, that is X, for which we calculate the anomalies. This notebook names dataset DSRIF-M and DSRIF-X accordingly. In this notebook, we are going to load the shapefile for African countries and selecting a single country. We are going to load the rainfall data and mask it to the selected country. We calculate the monthly rainfall anomalies and plot the results, aggregated over space as a bar chart. We calculate and plot the monthly rainfall anomalies partially. We are in our notebook. Before we start, we have to load the packages so that without those packages, we cannot run the analysis. So we are going to run all the cell of our notebook. So at any time, I will start from here. Once you have this blue line, that means we can run it and move down. Here, we have not run anything, it has not started, so we can see that it's blank. At any time we run it, it will give us a number. If it's the first cell to be run, it will show us as a code. So we load the package, and we know that under the package we are using, we have the data group of Digital Earth Africa. We have the NumPy, the pandas, the GeoPandas, the X-ray, the D Africa tools, and so on. So we run it. After loading the packages, we set up the Dask cluster. What is the Dask cluster? Dask cluster can be used to better manage memory use and conduct the analysis in parallel. For an introduction to using Dask with Digital Earth Africa, to have a more idea on the Dask cluster, we can go to the Dask notebook and Digital Earth Africa. Okay, So now to use that, we set up the local computing cluster using the cell below. So we run the cell below so that we can be able to use our DAS cluster. Is it we create our local clusters. This is where we are working. So this is the dashboard where we are working. The cluster, the work one, the core tools, and the memory we are using. This is now we follow the parameters that we need. First of all, we load the analysis tools. Now we are going to load the analysis parameters, which is made of the countries, the time M, the time X, the resolution, and the direction. Now, if we are running the notebook for the first time, keep the default setting below. This will demonstrate how the analysis works and provide meaningful results. So we talk about the time. Those are the parameters for our analysis. We have the time M, time X, resolution, and direction. The time M is 1981 to 2011. The SL 1981 and 2021. The time X is set the range of dates for the climatology. This will be the reference period M for the anomaly. So that means that we need a reference period. That's the M for the anomaly calculation. And standard practice is to use a 30 years period. So we have used 1981 to 2011 in this example. Okay, that's the reference period for us, 1981 to 2011, 30 years. The time period for monthly anomaly that we are going to calculate is X, that is 1981 to 2021. For the anomaly we are going to calculate. The ship has a spatial resolution of 5 kilometers and 5, and the size of the direction is X 500, Y 500. We run it. Now we connect to the data cube. Connect the data cube so we can access the GE Africa data. The application parameter is the unique name of the analysis, which is based on the notebook file name. So we connect to data cube. The app of Rainfall is Rainfall anomaly. We load our rain data. First, let's have a look at the product information for ships rainfall. We can see that it is stored in monthly time span, and its native resolution is approximately 0.05 degrees. So we load the product list. Is it? The rainfall shirts, that is the name. The rainfall estimate from rain gauge and satellites. Rainfall from rain gauge and satellites. The license, the defaults of our reference system. The default resolution. And we load data for long-term climatology now. This list. Using the analysis parameter defined above, we will load Shep's monthly rainfall data for the 30 years reference period. We load GM. These are our area of study, large, long, the long buffer, the large buffer. We combine the central large long with buffer to get area of interest. So we put in our query the dictionary, the X, the Y, the X, the time, the output SRS, the resolution, the measurement, and that's all. That is, we have 372 elements, X with 3 and Y 3. The time, the Y and the X. The spatial reference, 6933. We calculate now the monthly rainfall climatology. So all what we were trying to do since is just load the data. We load all the necessary data, we loaded the parameters. Okay, and at the beginning we show what is the standardized anomaly. Now we calculate the monthly rainfall climatology now. We want to capture both the monthly means, that is months, each month's average over 30 years, and the monthly standard deviation of rainfall within the country polygons for each year from 1981 to 2011. Firstly, rainfall is grouped by months and a mean is calculated. Then the standard deviation in rainfall total for each month is calculated. So to calculate it, we run our DF reference, the climatology mean, the climatology standard. We run it. Now, we've said it before, it will take a small time. We said it before that the crop needs water throughout the growing phases. So the availability of adequate water in the soil is essential to enable plants to grow rapidly. Okay. Sometimes in extreme cases where rainfall distribution is very poor, crop failure is normally high, which results in food shortage. For example, food shortages in many rural households that are actively involved in the primary production of cereals crop. When there's no water, there's food shortage. We all know that. Why? Because the crop needs water throughout the growing phase of his life. Now we can plot the rainfall mean climatology. This is the average rainfall over 30 years of each month. Now, climatology means will be run. And we plot it. We have the month 1, month 2, month 3, month 4, month 5, month 6, till month 12. That is our climatology mean, okay, of the rainfall. We have the value here. This is when we have this value is low. This is a violet value. The highest value is the yellow value. So we can see that the rainfall increases, attain his high level in the period in August. And from July, we can notice that the rain we have enough rain already. Even from here, in month of June, we have already up to 200 and above of rainfall. And in May, there's a rain already, but not too high. You can come under 150 and above, but not reaching the 200. Okay, so those are the dry season. You can notice that where we started noticing some small, that is the beginning of the rain maybe. I mean, we all know most of the time, the rain may start in March, depending on the zone where we are, March, April. towards the end of March, the rain will start and start increasing in April. In May, I notice it, and June, July, and August, the rain is at the high peak. Okay, so that's what we have now for our data that we loaded, and this is the climatology mean, just the rainfall mean. Okay, now we are going to load our data for the anomaly periods, but we notice that after August, there's a drop in the presence of water. The rain is dropping, and during November to December, that is the dry season of our area of study. January, we still have the dry season. February, the same thing. Okay. So when talking about vegetation, we are planting. When there's water, the plant will grow. Depend on the plants also. The plant will start noticing the plants because the soil is already wet, slightly wet, and the wetness of soil increases during the time. In May, you can notice it. June, and then our farmers can be happy, okay, because there's water, and when there's water, there's a vegetative growth of our crop. Load data for the anomaly period. Using the analysis parameter defined above, we will load the shelves rain data for the period over which we want to calculate anomalies X. We also need to mask this data set to the country polygon. We can recall at the beginning, we said that we have a global data, okay, and we are going to mask our data with the polygon of our area of study. We are loading the rainfall data for the anomaly period, matching the spatial essence of the climatologies. We load our data from the shapes, the rainfall data from the shapes monthly. The time, the task, we mask with our country polygon. We calculate the standardized anomaly now. We can visualize the anomalies spatially and see if they are associated with certain landscape features. Do the spatial anomalies shown in the plot below align with the aggregated anomaly shown above? Let us see. Do the spatial anomalies shown in the plot below align with the aggregated anomalies shown above? You can see loading. When it's loading, look at the color of this area. Let me see. Yeah, it's loaded. So we plot the average rainfall anomaly across the country. Below the spatial mean is taken so we can present the monthly anomalies aggregated across the selected country. So below we have the partial means, and below we plot a bar graph that will show the average rainfall anomaly across the country. We plot our bar graph. That's the monthly standard rainfall anomaly. And we have here, we can read standard deviation from monthly rainfall. Okay. The minus are in red and the plus are in blue. And we have 1980 January, 1985 January, January 1990, January 1995, January 2000, and January 2020. Okay, so this interval is 1 year interval. What do we notice here? We notice that there are some periods when the rainfall, the standard deviation from the monthly mean is very low, and those are high. Okay. Now, what we have is across the country. Standard deviation that we have, standard rainfall anomaly, what that we have is across the country. Now, what we have, when there's a rain, we have the standardized rainfall anomaly of the country. Now we need to know, how does the pixel, how did they react? Because when talking statistically, when you have a population, is the high population that we use as an example. But in between those population, there are some elements that shows some other aspects that have other information to give us. That's why we went down to per pixel plots of the rainfall anomalies, so that we can calculate the average anomaly across the entire country, obscure detail on how rainfall anomaly are spatially distributed within the country. Below, we enter a start and end dates. That is within the time S range. We enter in the analysis parameters section to plot per pixel anomaly for the range of dates we specify. We select the time range. It starts at 220 in July. We end at 221 in June. So that is the time we are going to plot our rainfall anomaly per pixel. We plot per pixel anomaly. We run it. That is it. After we selected the time range, now we plot per pixel anomalies now. We notice that the start date is July 2020 and the end date is June 2021. We can read here 220, that is July. Okay, that we were calculating the standard anomalies per pixel. So look at the legends. When the color is brown, dark brown is -1, moving to blue, light blue. When we have 0, 0. So that's the rainfall, actually, the anomaly or per pixel. So there are some pixels in July that is showing us the highest level of wetness. Okay, that means there's water in some pixel during that time. This pixel, for example, can reach the peaks of our rainfall. That is above 1. But we still have some pixels that behaves differently. That is about 0, though some are above 0. When we come to the August of 2020, this is another precision we had. We can see that there are some areas that are completely dry. Okay, here we can go, is above, is between minus, let's say above 0. No, it's not above 0, it's below 0, right? So that is what we have, the value we have here, pixel. So we notice that all the pixels are not acting the same way. All the pixels are not getting the water the same way. Okay, so this is important sometimes depending on the resolution of our data, depending on the resolution of our pixel. Okay, so we can accurately give a reason why some areas are growing and why some areas are not growing. Okay, so moving to the next month after the September, we notice it here. December, they act differently until we come back to 2021, June, showing that there's dryness in the area. Almost all the pixels are dry. Okay. So distribution of rainfall is key, as good distribution pattern ensure that moisture in the soil is adequate to support plant growth throughout the growing season. And even distribution of rainfall promotes rapid growth of the plants. So from here, as I was saying, that when in a population, when talking about statistically, we took much of the time of the mean of the people, the major people that behave the same way. But here, per pixel is trying to show us how each element behave individually. That is per pixel that we calculated. So rainfall is very important for our study when talking about agriculture and food security. Okay, so the threat of food insecurity has increased as a result of the phenomenon of climate change. So we need to have those information concerning the parameters. So this is the second parameters that we are working on our module of agriculture and food security. If there's a question.
Yes, thank you so much, Jamie. There's a small question from Bako about how you can be able to distinguish the wet and dry areas. So possibly one of them will be if we could have some area of choice, like if you're looking at Ife, and possibly if there was some ground information, that could be a way of also distinguish the same. But also from the resolution of the data, the question is posed to you, Jamie.
Yeah, let me get in the question correctly so that I can give correct something. Let me go back. It is a way to better distinguish wet, that is blue, here to dry, that is red, here from 1981 to 2021 within the identified area. Is a way to better distinguish wet. Actually, I believe that in each area, we know already the climates of those areas. if there's a change, that means that there's a variation. There's a variability in the communities. We know that, right? So we distinguish. Let's go back from the presentation of Baku. Let me go to the where the question is coming from. I hope this is where, Mr. Baku, is it this question? Because the other one is 20, is not starting from 91, 81, but starting from 220 to 221.
He mentions the next one
The
because he's
next
currently
one,
in a meeting. Yes, thank you.
okay, the next one is per pixel. And the year we did not start from 1981, we start from 2000 to 2021. It will, if we start to 1981 to 2000, it will be very difficult to, data will be so much because we are talking about pixel related data. Okay, let us explain it, changing the year of 1981 to 2020 and explain it with that. Is it necessary? I think it's necessary. That is there any way to distinguish wet that is blue from the one that is red? Is it so? Is it the question? Because I did not get the question very well.
Yes, it's per pixel. So like looking at cell number 16, the results.
Yes.
So here we have the different months. For example,
this is
July to...
This is July, this is August, this is September, October, November, December of 2020. 2021, this is January, February, March, April, May, June. Okay, so how can we distinguish the blue and the red? The blue is wet. When we look at the legend that is here, it's from the legend that we confirm that the blue is wet and the red is dry. So on our pixel, if you can see the color that is brown this way, because the legend moved from -1 to 0. So if we see the color is blue, that we can confirm is wet. If the color is brown, or brown or dark brown, you can say that the area is dry. Now, my question to so that I can give more explanation is that, is it because the legends, you could not be able to see the legend before that you ask the question, or there is something that is bothering you so that I can get it very well?
So he mentioned it was about the graph and this particular index. And also I was trying to see, there's a link which I've put in the chat, which also helps to compare what we get. So it's a comparison because of the CHAPS data and also the data that we have from the colleagues from WFP who have vulnerability assessment ranging from the similar data source. And it gives you a comparison based on whether we received rain or not. And I think this is just the explanation that, for example, we could compare with what agreement collects if there was no rain in June. The rain season starts in the start of July. Then also we have surprise seasons where we have exceptional rainfall, like in September and October. So it's also more of what we can compare with our regional Met agencies so that we don't burden Yajemi with this heavy question since it's not a PhD defense. So just to save you from that question. Then also,
I would like to understand better the question because I did not get it very well, actually.
Yes, so for this explanation, it is more of what we get from these results and what we can compare with the regional Met agencies, for example, in Nigeria or in Niger, or also the seasonal forecasts that we get from different partners like GeoClam. So this is just some information that we can add to verify what we are getting. And we'll also discuss this offline in another discussion just to improve the results of this notebook. So I wish also to welcome other colleagues who have any question or comment. And first, as we continue, is to clap for Yajemi for being our able professor today. also welcome any questions from colleagues and partners, and also recognizing our participants from the Africa Women in GIS who are here. They are going through a small mentorship program, and they finish soon in October, and some of them will also come one day and present to us. So thank you everybody for joining us. Any question for Yaje?